My asymptotes of the secant function. Asymptotes is a weird word. The spelling of it is weird. Like the pronunciation and spelling don't seem to go well together. That's the word. Asymptote. Whatever. Say it fast, no one will know if you're saying it right. All right, so I did the asymptotes. Now what? Kind of the same thing, right? We're going to draw a dot. How about at the bottom of this valley? We should have a dot. Now, there is something a little different here, though, because we only have like half of these, don't we, in our drawing? But we know at the top of this hill there's a dot. And we know on top of this hill there's a dot, right? I think the bottom piece of this one's pretty straightforward. You just draw your little U-ish looking thing in here. Like that, and we're good. But there's more to this graph. Over here, what's going to happen if I draw this to the right towards that asymptote? Where should my secant function go? It should go up. So you're getting like that. Now, is there another side to this? Absolutely, but if I'm just drawing one period of cosine, I'm not going to see that. But technically, it's there. This graph does continue backwards. We do have another vertical asymptote, and we do continue this, all right? On this side at 2 pi, it's going to come to the left and go up like that. And again, we do have the other part of this, but if we're just drawing between 0 and 2 pi, this is the picture we're going to get. Questions? That's the graph. What's the domain of the standard secant function? This one's tricky. I like this one. What's the domain? X can't be what?
N pi over 2.
X cannot be n pi over 2. Okay, let me see if I can't. I'm not saying if that's right or wrong yet. I'm going to see if I can get everyone on board with this. Do you remember the unit circle? Yes, of course you do. All right, so where are these things happening? Pi over 2, right? Which is here. And where else are they happening? Next one is at 3 pi over 2, right? And the distance between these is pi, because what, that's a half revolution? So these 2 points represent all the places we can't be, right? So how could you go from this point to this point, back to this point, back to this point, back to... See, there's something wrong with this formula.
90 plus pi n. No?
Yeah, but you're using degrees and radians at the same time. I'm not...
Oh.
Okay, this was one of your test problems, and I don't think I stated it clearly enough, but we did this in the beginning of the class, like when we were first talking about angles. If I want to represent these 2 points, all the possible angles that correspond to those 2 points, then I first start out by getting myself there. How do I get myself there? I need my angle to be pi over 2. Now I need to go from there and be able to jump here and then back, and then here and then back. And that's a rotation of pi every time. So I'm going to say plus n pi. Plus n pi. Do you all remember me telling you that this was very important? We are getting to the point now where it's going to be stuff you have to be able to do. I tried to introduce it to you earlier, but now we need it for sure. Now, one little caveat here. X can't be that. Scrap that. X can't be that, right? It's our domain. We're telling you what X can't be. It can't be pi over 2 or 3 pi over 2, or 5 pi over 2. Any of those won't work. I would like, if you don't mind, this right here. If you do not understand that, please put a star next to it. Please come see me in my office because, I mean, you are going to suffer on the next quiz test if you can't do that. It's going to really hurt your grade. So let's sit down and make sure you're clear with it. I'll give you like 5 or 10 examples, and you can just, once you get it, once you understand it, you'll be good. Okay, all right, that's domain. Does anybody want to try and tell me what it would be in interval notation? No? Pi over 2. How about here? 3 pi over 2. Okay, good. And now you just need to jump by how much to move over? To take this interval, to jump it over, you have to by n pi. Now, how do you know the distance between here and here is pi? Well, you could subtract, but just look at it. This is pi over 2, right? Isn't that 3 pi over 2? Isn't that pi right there? Okay, so plus n pi, plus n pi, n pi. So that's going to start you at these 2 points and then just jump you over by pi each time, or jump you backwards by pi each time. How about the range? Negative infinity to negative 1, 1 to infinity. Same thing as cosecant. Exactly the same. How about, not domain, how about period? Same as cosine, 0 to 2 pi. Because it's going to start repeating this picture. Right? If I took this, took a copy of it, right click, copy, over here, right click, paste, put it on there, it would continue the same picture over. Okay. It's 12:10. I've got half an hour. I still got quite a bit to do here.
Are you going to want both intervals on the domain?
I'm not going to need these on a test. This you'll have to do though.
Right.
Yeah, but this you don't have. This is just, again, trying to push you to think a little bit about it. All right, so what about this? If you were asked to graph -4 secant of 1/3 x, how would you graph that? How would you graph that?
We do it like a cosine.
You switch it to a cosine, right? Because it's secant. Secant's the reciprocal of cosine. So I'm going to just really give myself this problem to graph. Okay, I'm just doing this quickly. I already set that equal to 0, and I set it equal to 2 pi, and I solved it mentally. I'm trusting you could do that, and you could get those, and you could split them in half and get all that, right? Given enough time, you could get that, right? And then you have your x-intercepts, which come in at the 1/4 mark and the 3/4 mark. Why? Because it's a cosine, right? And then you have to go and plug in a test point. I forgot to put 0 here. But you could plug in a test point. When you did your test point, you would determine that it actually does -4. It goes like this, and then like this, and then like this. So I went fast through that because that's what we did last class, and that's what you did for homework. So maybe that takes you 10 minutes. I don't know. Whatever. But you get to it, right? Once you have that, now you're ready to graph secant. To graph the secant, you just draw your vertical asymptotes, and you draw your little parabola-looking things in there, and you're done. Vertical asymptotes come in at the x-intercepts. This little u is the easy one because you got that full hump to work with there, right? So you put the full u in there, and then it's these two that you only get the halves. So I would say that if I were going to give you a test question, it's probably better for me to ask you to graph secant than it would be to ask you to graph cosine, because you're going to have to graph cosine anyway if you graph secant, right? So I would be surprised to see many problems that involve just sine and just cosine on the test. I'll kind of kill like two birds with one stone. I'll just ask you secant and cosecant, right? And then you have to do it. So these aren't so bad. I mean, it's just really one more step added on at the end. Draw your vertical asymptotes, draw your little u's, and you're done. Let's talk about tangent. Now, tangent's going to be kind of a little bit of, well, it is a game changer. It really is different than these others. And for this, I'm going to, again, ask you to think about something. Remember how I was asking you to think about, like, what if you have 1 over a small number, and you said that that would be a big number? Or if you did 1 over a big number, you said that that would be a small number? What would happen if you have a small number over a big number? And what would happen if you have a big number over a small number? So small number on top, big number on bottom would result in what? Small. You could take an example. Give me like 1/100th. That's small, right? Put that over 10,000, let's say. So you have a very small number, and you're dividing it up into a bunch of smaller pieces. So they get even smaller. So small over big should be very small, tiny, right? Okay. And then what happens big over small? So take a number that's big, like 10,000, and divide it by like 1/10. Wouldn't that flip up and multiply that by 10 and get bigger? So this would start becoming, I don't know how you spell this, ginormous. Is that a word? That's not how you spell ginormous. It is? Really? I'm going to ask my daughter tonight. I have an 8-year-old that's really, she loves spelling, and I'm going to ask her if she knows how to spell ginormous.
Maybe it has an A, whatever.
No? I trust. Okay. Whatever. It's a weird looking word. Ginormous. All right, got that? Small over big, small. Big over small, big. What is the definition of tangent? It's what over what? It's sine x over cosine x. So let's graph sine and cosine together. All right, here we go. And you know what? I think I'll color code these. Nah, I won't. Okay, here we go. Okay, here comes sine. There's sine. Yeah, I'll do at least cosine. I'll do that in red. Cosine. What am I doing? Okay. There it is. All right, let's get some technicalities out of the way first. This function is, y'all with me? Okay. Well, everyone's still writing, so I'll give you some time if you need a second. If I go too fast, just let me know. All right, so let's get the technicality out of the way. This function is undefined whenever cosine is 0, right?
Right.
If cosine is 0, this function is going to completely fall apart. That means anywhere where cosine is 0, so anywhere where I have the red function hit the x-axis, I've got major problems, right? So I know right away, here and here, I'm going to have asymptotes for tangent. Right? So the green is going to be tangent. The red is cosine. I told you I wasn't going to color code it, but I guess I am. And the blue is going to be sine. All right. So let's start talking about what's happening. Let's start, how about right here? Here's an asymptote. Here, let's go right in the middle, right there. Okay, so if I take this value, which is pi, isn't it? And this one was 2 pi. This was 3 pi over 2. This is pi over 2. So if I go to pi, what is sine of pi? 0. Okay, so I would have 0 on top, and what would I have on the bottom? Cosine of pi, which is -1, right? So what happens when you take 0 and divide it by -1? You get 0. So my tangent function should be 0 here. So I actually have part of my graph here, don't I? By the way, these are not dots, right? These are asymptotes. Do y'all follow that? That at pi, tangent is 0.
You have to re-explain that one again.
Okay, I will. If I wanted to know what tangent of pi was, then I'm doing sine of pi divided by cosine of pi. And if I go and I look at sine, here's my sine curve, right? At pi, sine is 0. So the top is 0. And then cosine of pi, which is the red one, is down here at -1. So I get -1 there, and that gives me 0, right? Okay. Now, let's start moving this way, all right? So if I pick a value, this is going to be interesting. If I pick a value here and I plug that into sine, what am I going to get? So I'm trying to plug it into the top first. If I plug that value into sine, I'm going to get a positive number, right? And then if I plug it into cosine, I'm going to get a negative number. And when I take a positive divided by a negative, I'm going to get a negative. So do you agree that at that little x mark, tangent should be negative? Yes? Okay. I don't know where it is, but I'm just going to put it like right there in the little negative, right? With me? Now, I'd like for you to move closer. Let's go like right here. I plug that into sine, I'm going to get a what? Positive number, right? Now, it's a bigger positive number than it was here, wasn't it? That is a bigger positive number, but what's happening on cosine? It's negative, but it's actually what? Smaller. So I've got a bigger positive number over a smaller negative. Remember we did big over small? Big positive over small negative should become big negative, right? Big negative. If it seems weird that I'm talking like this, like big positive, big, I mean, this is really like, calculus is a lot like this. You have to think about behavior of function as opposed to like plug 2 into this function. It's different. You're trying to figure out how things are behaving. So at this x, I should get a negative number that is actually bigger negative than this one was. Let's get even closer. Here, I've got a sine, right, that's bigger than it was just a second ago. And I've got cosine, which is still negative, but now it's even smaller, which means now this number has to be even bigger negative, right? And so it's got to be down here. And, well, I mean, you can kind of tell from the behavior, it's going to be asymptotic. And it's going to go like that. What will happen on the right side? So we could start plugging points in and doing the same thing. We have a negative number over a negative number, don't we? So it's positive. And then let's go all the way over here. Sine first, right? This is a pretty big negative number divided by a pretty small negative number. Big over small is big. Negative over negative is positive, though. So I get a positive, big positive. And so we've got this. I missed it. I just moved the point over. There we go. Fixed. That's the graph of tangent. It's a pretty boring function, actually. I mean, when you look at it, it's pretty boring.
It looks kind of exciting.
It's good. It's good.
It's just that, I mean, it doesn't have any, like, curve to it. It just, right, just does this thing like that. Now, it's going to repeat itself. Like if I move out over here, it's going to do a repeat of the same thing. Yes, exactly the same. So if I were to come out more, have another vertical like this, it's going to go through like that. Right.
So then on the left side, we're only going to have that the half of tangent coming out.
Where? Over here?
Yeah.
Yeah, we would, at 0, we would have 0. And then it would just be this side like this, right? Okay. Now, I'm not done. I'm not done. I just want to make sure everyone understands kind of the basic shape of what tangent looks like. Yes? All right with that? Okay. Now, because of what's coming later, which are what we call the inverse trigonometric functions, we are actually not going to use this one as our standard place to look at tangent. We are going to just back it up one period and look at that one as our standard one. Okay? It was just easiest for me to draw this one off of sine and cosine, but the one that we like to use as like our basic tangent is the one that we would draw right in there. So I'm just going to erase this and draw you what tangent looks like. Well, one period of it. If you draw your xy axes, you're going to have vertical asymptote at pi over 2 and also back here at negative pi over 2. These are where your two asymptotes occur. At 0, your tangent function will pop through 0, and then it will look like what we just graphed a second ago, like this. This is y equals tangent x. Now please understand, it does it again and again this way, and it does it again and again this way. But that's the one that we really like. The one I drew right there, that's the one we're going to spend most of our time dealing with. That piece. When you graph these, like if I were to give you this example, to graph y equals, let's say, 5 tangent x, this becomes difficult to graph. Let me illustrate why. 5, with sine, it did like an amplitude, didn't it? It like stretched it out with sine and cosine. But with tangent, it still stretches it, but it still looks like this, right? It's like every point gets multiplied by 5. So would this move? No. Now this one right here would get multiplied by 5, so it would go up a little bit, and this one would go up. But at the end of the day, it would still look like this basic shape. Yeah, it's like almost like zooming in or out. I mean, it really does not, it's hard to draw it, in other words. So when I ask you to graph tangents, all I want, even if I put a 5 in here, and you'll see this on the homework if you do the homework, My Solutions, is that I don't care too much about that 5 in front in terms of the picture. As long as you get this basic shape, we're good.
To annotate it, how would we annotate it to show, like, I mean, yeah, we'd get the same shape, like you said, the basic shape, like, we just plot it the same way.
Yeah, I'd plot it. I don't care about, that's what I'm saying. I don't care about that stretch out. I don't care about it. Okay, let's take a look at cotangent. All right? I'm gonna go right to cotangent now. And then I'll maybe be able to do one example I really am interested in doing. All right, cotangent x. The only difference between tangent and cotangent in terms of the setup is that it's cosine x over sine x instead, right? It's flipped over from tangent. So if I draw sine and cosine together, that's sine and cosine like I did before. Where am I now going to have the vertical asymptotes occur? Well, where is this thing undefined? When sine is 0, right? And sine is 0 at 0. And where again does it happen? Pi. And then again here at 2 pi, right? Do you see the difference? Instead of being at pi over 2 and 3 pi over 2 like we were, it's now at 0 pi and 2 pi. Yeah, that's going to be a little easier to work with. Now, you know how I just showed you that on tangent we like to use the standard one that goes between pi over 2, right? Negative pi over 2 and pi over 2. That's our standard one for tangent. The standard one for cotangent is the one that goes between 0 and pi. And we just don't even worry about this part at all, okay? Just in here, if I were to do all those little ratios again, which I'm not going to do that, big, small, negative over this, all that, forget that. I'm just going to draw the picture of cotangent, what you would get. At pi over 2, you would have 0. Why is that? What's cosine of pi over 2? 90 degrees. Cosine's the x-coordinate on the unit circle. You get 0. What's sine of 90 degrees? You get 1. 0 over 1 is 0. So that's why we have that. And now it's actually going to be the opposite of tangent. Instead of going like down then up, it's actually going to go like this. That's your cotangent. Let me pass around the assignment sheet. We're not leaving yet. Hold up. I have to do an example of each of these. Here we go. All right, 2 examples and we can call it a week. We're getting closer and closer to spring break, aren't we? Starting to feel like it, isn't it? Outside, the weather. All right, here we go. Examples. Y equals -3. Tangent of 4x. Now, when we did sine and cosine, the standard approach, the first step was to set the argument equal to what? 0 and 2 pi, right? That's the standard approach for sine and cosine. For tangent, the standard protocol is not to set it equal to 0 and 2 pi. Instead, equal to those two very important places we have the asymptotes. So we are going to set 4x equal to -2 pi and 4x equal to pi over 2. Did I say 2 pi? Negative pi over 2 and pi over 2. Now, that goes back again to the picture that I gave you, the one that we really like to work with. Pi over 2, negative pi over 2, standard tangent function. You have to remember this, okay? That pi over 2 and negative pi over 2 is what you use for tangent. And then you solve these. So what do you get here if I solve for x? Divide both sides by 4. Negative pi over 8. You all happy with that? This one over here, x equals pi over 8. Now, I'm going to draw a graph. And all I have to do is put pi over 8 here. Negative pi over 8 would be on the other side. I'm going to draw myself two vertical asymptotes here. Right in the middle of them, I'm going to put a dot. And then I'm supposed to draw this thing that looks like that, right? But I have a negative here. So with sine and cosine, I said now you plug in a test point and you try and figure out what it is, right? For tangent and cotangent, you are safe to just use the negative or positive here to determine what's happening. If it's positive, it looks like this. If it's negative, it flips over, which means that the part that went up now goes down, the part that went down now comes up. So it's going to look like this. And the 3, again, I don't really care about. That looks like a cotangent, doesn't it? But it's not, because where we have our vertical asymptotes are different than what we would have with a cotangent. So tangents and cotangents, they look like each other, like flipped over, they look almost the same. But it's where they actually have the verticals that makes them different. Yes?
The cotangent one, we have it on past the 0.
Well, on cotangent, if this was cotangent, you would set these equal to what? Instead of this and this, you would do what? 0 and,
2 pi.
not 2 pi. Go back and look at the picture. 0 and pi. Okay, so that's what's happening. With tangent, we're always going to set the argument equal to those two. All right, with tangent, we will. With cotangent, let's do cotangent right now. I was going to do an example, but I'm done. Okay, that's it with graph. You don't have to go any more detail than that. Is that fair? Okay, let's do the same problem. You know what? I'm going to leave this one up here. And I'm going to do the same problem now, but I'm going to change it to cotangent, just so you can see the difference between the two. Cotangent of 4x. So negative 3 cotangent of 4x. So because it's cotangent, I have to remember, like in my brain somewhere, I have stored that I need to set the argument equal to 0 and pi. Okay? So 0 and pi are the ones that I use with cotangent. So sine and cosine, 0 and 2 pi. Tangent, negative pi over 2 pi over 2. Cotangent, 0 and pi. And unfortunately, that's it. We're done. Like, we don't have to remember anymore. Those are the ones. And then when we solve these, we're going to get some nice answers here. We get x is 0, nice. We get x is pi over 4. And when I plot those, that's going to be different than this, right? Pi over 4 is actually out here. And 0 is here. And we would have what happening at pi over 4 and at 0? Asymptotes.
It's negative, it's flipped.
It will be flipped. And then between these two asymptotes, right in the middle, I have the x-intercept. And it's supposed to look like, basic cotangent functions are supposed to look like this. That's what a cotangent looks like. But because it's negative, it's flipped. So this side comes up and that side goes down. So it's going to look like this. I know on camera the purple and the black look exactly the same, but can you all see the difference between these two graphs? The black one is the tangent version of that, and the purple one is the cotangent version of that. Yes? So look, if someone were to just come in off the streets, I'm sure this would happen to you, probably happened this weekend. If somebody were to just be like, hey, check this out. You see this? See that right there? And they don't tell you anything, just that. Can you say, well, that's obviously a tangent function? You could say it could be a tangent function, right? But it doesn't have to be. That could be a cotangent function. It could be. It just, if it's flipped and moved properly, it could be a cotangent. So Man, I had a problem that we don't have time to do. That's definitely enough to get you through the homework, though. How do y'all feel about this? Gonna have to practice, right? Sign-in sheet. Sign-in sheet's up here. I think we're done. I really am trying to get the grades updated. But like I said, I made hours of videos yesterday and trying to stay on track with the videos right now.